Okay. See how the monitor does up there, but welcome everybody. And good morning. It's great to see all of you. Sometimes in physics and quantum mechanics, we have a mixed state of things. You can have a particle that has spin up and spin down until you observe it, and then you collapse the wave function. They talk about Schrodinger's cat being both in an alive and dead state. And sometimes I feel like the COVID-19 pandemic is in a mixed state. Because in one sense, it's gone. Like if you read the news, I don't see any news about it. There's no like lockdowns or school closures or mask mandates or anything like that. But on the other hand, everybody's getting COVID. And my son's in grade 4 and he has 23 students in his class. On Monday, there were 12 of them missing because they all had COVID. And my TAs keep getting COVID and my colleagues are getting COVID. And so it's sort of weird. It's here and it is not here. So at the same time. Today we're continuing on with chapter 7, and we're going to try to finish it up on Friday, actually, so that we can get on to chapter 8 next week and finish up chapter 8. Then there'll be reading week, and then we'll come back for the test, term test 2. So we'll start talking about that and the schedule, how that's going to go. Maria's here, front row. She can read your, if you go on Ed discussion board and type in classes, you can even post anonymous anything if you want. Any questions you don't want to shout out at me, you can get Ria to read them out with the microphone. Or you can just shout out at me also, that also works, but my hearing's not so great. Okay. Ria, are we good? Good to go. So this is this idea of gravitational potential energy, of stored potential energy in this tennis ball, for example. If it's sitting up here, if I release it, trigger it somehow, it can gain a bunch of kinetic energy. So it stores the work done against gravity. Another way of putting that is that if I pick the tennis ball up and push it up, push, I am applying a upward force to the tennis ball, and I'm moving it in an upward direction. So the displacement and the force are in the same direction. So I'm doing positive work. And that stores the energy as, it's called delta U sub G equals mg times delta Y. Meaning that you change the Y position, you change that gravitational potential energy. So that's your definition equation for gravitational potential energy. And it's true as long as, I guess, the gravity force is just mg, and that's kind of constant. So you can't change y very much. Like you can't change y by 3,000 kilometers or something, because then the acceleration due to gravity would be a little less as you get farther away from the center of the Earth or something like that. But it definitely works in like room-sized lab environments. And one thing to note is that delta means that this equation and this definition only deals with the changes in gravitational potential energy. There is an arbitrary 0 point where it doesn't matter where you put it, as long as once you define the 0 point, you're consistent. So you can place the origin of your coordinate system and thus the 0 point of potential energy anywhere you want and still get the correct answer to the problem using this work energy theorem stuff, work and energy. And the reason is that physically it's only the change in gravitational potential energy that matters. It's a quantity whose change is related to something physical, but its absolute value doesn't have a physical counterpart. So here are two people, Amber and Bill, who disagree about the 0 point of potential energy. So, and there's a rock floating in space 1 meter above the ground, and Amber defines the ground to be zero height, and so she says, hey, look, that rock has 9.8 joules of gravitational potential energy. But Bill has defined 0 meters to be the initial position of the rock. I guess the rock is about to fall. So he says, hey, this rock has 0 joules of gravitational potential energy. So the question is, who is right? Well, what will happen is that the rock will fall, right? If this is initial, it'll fall down to the ground. And from Amber's frame or something, or reference frame, you've got kinetic initial plus UG initial plus the work is equal to kinetic final plus UG final. That's your standard work energy equation, which you always use. And what happens is if it's released from rest, she's saying it's got this initial plus 9.8. There's 0 work done on it, and at the end, it's going to lose all of its kinetic energy, all of its potential energy, and convert to kinetic. So she'd say that 9.8 is equal to 1/2 mv final squared. Whereas, and then she'd get some answer. Just before it hits the ground, it has 2 times 9.8 divided by the mass of the rock, 1. Whereas for Bill, let's do Bill's frame. What he says is that same equation, kinetic initial plus UG initial plus external work is kinetic final plus UG final. He's saying it's released from rest. It's released with 0 initial potential energy. There's no external work. And then he says that what goes on here is that it ends up with negative 9.8 joules at the end. So he would just say that 0 is equal to 1/2 mv final squared minus 9.8. And to have the same thing, v final is the square root of 2 times 9.8 divided by 1. So they both get the same answer, but just for different reasons. They've just set the arbitrary 0 point to be different. So this is a whole other way of looking at free fall. Instead of things accelerating downwards with this 9.8 meters per second squared, they're still doing that. But what you can think of is there's an initial position, which is high, a final position, which is low. As the thing changes its position, it's changing its gravitational potential energy, that's decreasing. And so to conserve energy, it's increasing its kinetic energy. And you get the same answer, which is 9.8. But it has some nice shortcuts that you can take. Sometimes questions that look very difficult, if you were to think of them in terms of kinematics and chapter 3 and 4 methods, become very simple when you look at them through the lens of chapter 7 and just conservation of energy. So you have 3 balls, all of which are launched with the same initial speed, vi, but they're in different directions. One is launched upwards, 45-degree angle. Another is ball B is launched directly horizontally, initial angle is 0. Another is ball A is launched downward 45 degrees. They travel along their different paths, and just before they hit the ground, they have some final speed, v final. So how do you rank those speeds? Which one has the highest speed just before it hits the ground? Give you a minute to work on that. Just a minute. Think, pair, and share with your neighbor. So that's the time. see what survey says. You guys want to click in? Click in a guess is fine. Remember, it's 0.8 points just for participating, and the extra 0.2 for getting the answer right on the first try. Going once, going twice, and stop. Survey says sort of 70% saying they all land at the same speed. So this is a chapter 7 concept. It's you don't have to do, I mean, you could work it out with kinematics and projectile motion, all this stuff, you get the same answer, but it would take you a long time. What I'm saying is that HI is the same for all 3 balls. And we even say that VI is the same for all 3 balls. They're shot at different angles, but if you look at the equation for kinetic energy, it's 1/2 mv squared. There's no angle in that. It doesn't matter what angle you shoot it off at. So if you just think in terms of conservation of energy, and also H final is the same for all 3 balls. And remember that the kinetic energy plus the gravitational potential energy is conserved here. There's no external work. So G final. So you can kind of look at that as 1/2 mvi squared plus mg times the h initial equals 1/2 mv final squared plus mg h final. So they're going to have the same, since vi, hi, and hf are the same for all 3 balls. I think v final has to be the same for all 3 balls as well. Masses will all cancel. Let's do, I mean, this is a little bit of a trivial example, but I said that free fall can be looked at as a conservation of energy equation or thing. So let's say I hold a ball at some distance 5 meters above the ground. So maybe the initial system is this, V initial equals 0. And I release it from rest. How fast is it going just before it hits the ground? So there's the final. I've got to touch in the ground, but there should be a little gap there or something. V final equals question mark. And we say H initial is 5 meters and H final equals 0. So you do, sometimes I forget to put this plus W, like external work or something like that, is equal to the final energy, because this is 0 most of the time. So you've got, it starts from rest, it starts with some big potential, no external work, ends up with some speed and 0 potential. So I would just say 0 plus mgh initial plus 0 is equal to 1/2 mv final squared plus 0. So G, if you, I guess, cancel the m's on both sides, divide both sides of this equation by m. This is a 0, by the way. Most of the terms in this energy equation are usually 0. I write them down anyways, just to sort of gather my thoughts. And I get V final equals square root of 2gh, which is the same equation you would have got if you had just used kinematics. But it's a different concept, and sometimes, as I say, if there's angles and everything involved and you're given speed but not the angle, you can use this equation to, or this method to solve problems you wouldn't be able to solve using chapter 3 and 4. 9.9 meters per second. Okay. Let's do one more learning catalytics. This is a weird one. So a hockey puck sliding on smooth ice, so frictionless, at 4 meters per second, comes to a 1 meter high hill. Will it make it to the top of the hill? Yes or no? Or can't answer without knowing the mass of the puck, or can't say without knowing the angle of the hill. So this is one that would be impossible to do with kinematics because you're not even given any of the details of this angle. You're just told that there's a hill, it's 1 meter high. I'll give you a minute. This one, you might have to actually work something out. 4 meters per second and a 1 meter high hill. I'll give you a minute. How are we doing, guys? Something to do, it's going to have to be 1/2 mv squared, and you're comparing that to mgh. 4 squared being 16. Yes or no? Going once. Going twice. Do survey says. "65% of you voted for no," but the question is really why, right? I also think it's no. So why? Well, so first of all, I guess I've got, let's use K initial plus UG initial equals K final plus UG final. Oops. So it starts with 1/2 mv initial squared and plus 0 initial energy. And then final, you don't know, plus mg times the h final. So you don't actually know the mass of the puck, but I guess you could solve it out so you could divide both sides by m, and you could say K final over m is equal to V initial squared over 2 minus G times H final. And this, I think, has to be greater than 0, because the mass is greater than 0 and the kinetic energy is always greater than 0. So that's one thing. So you can actually work this out. You get that it's 4 squared, right? 4 squared over 2 minus 9.8 times 1. And I got it's 8 minus 9.8. So it's negative. And that's not possible. That's one way of solving this. So in other words, there's not enough initial kinetic energy to get it all the way up to 1 meter. It'll turn around once the kinetic energy goes to 0, and it'll start the opposite direction. Okay. How are things doing with the discussion board, Ria?
There's just one question,
okay.
And it's, is energy always conserved such that E initial equals E final, except in the case of friction?
Yeah, well, even with friction, E initial can be E final, depending if you include those surfaces in the system. So the book talks a lot about this. So first of all, I keep on forgetting that E initial does not equal E final if there's external work done. So if someone else is pushing on the system, some external applied force, and doing work, either positive or negative work, then that will change the total energy of the system. So that's one thing. But that's a great question about friction. You can think of friction as an external force, in which case then, yeah, this work external would be due to friction. It usually slows things down. But we're going to talk about this pretty soon. Let me just finish up this potential energy stuff. I actually want to do springs first, and then friction, and then we'll be done. So let's start with springs. Elastic potential energy. So if you take a spring and you stretch it with your finger, then you are doing positive work on the spring. And so how much work are you doing? Well, Hooke's law is F equals kx, the force of your finger on the spring, is proportional to how far you, so spring constant's k, and then x is how far you pulled it away from equilibrium. So you could do work as kx times the distance, but unfortunately this is wrong. Why? Because k is constant, but x is not actually constant. If you start from equilibrium and then stretch it out to a distance x, x has varied between 0 and its final x, which is x here. So it just says, but keep in mind that the force the object exerts actually starts at 0 and then increases to kx, so you have to cut that in half. So this is correct. There's a 1/2 there. And you could solve that using an integral, I guess, but we're just going to say that it's 1/2 kx squared, because we're not doing calculus in this class. The work done on the spring is equal to the energy you put into that spring. And this is a form of potential energy. So once a spring has been stretched or compressed, it stores energy, which can then be used for something. Similarly to how if you have this coffee cup sitting right at the edge of the table, I'm a parent, so I never like to see like cups right at the edge of the table. It has potential energy. Something bad could happen if something shakes a little bit. Similarly, Lillian has set up this mousetrap here, which is a loaded spring. So there's a spring here which is totally loaded. So if I were to, and there's a bucket full of ping pong balls, so if I was to touch it at all, give it a little, nudge, I could release all the ping pong balls and make a big mess. Stored elastic potential energy can then go and turn into kinetic and shoot ping pong balls all over the place. Thank you so much, Lillian. All right, so continuing merrily along, a compressed spring stores energy. So we're going to do, again, initial versus final. The spring has some initial length beyond its equilibrium and some final, and you can define the stored potential energy to be a positive number. This is positive. Sort of like kinetic energy is always positive. And it's 0 when the end of the spring is at its equilibrium length. So right now, this spring here, which you can't really see, is at its equilibrium length, so it doesn't store any energy. So it's not going to do anything exciting from here on. Oh, there it is. All right. So let's try to work this out in an example. A moving car has 40,000 joules of kinetic energy while moving at a speed of 70 meters per second. So instead of giving mass, it just gives you the kinetic energy. A spring-loaded automobile bumper compresses 3 meters when the car hits a wall and stops. So I'm going to try to draw this. There's a wall, and there's a spring. And initially, the car is moving along. Okay, this is the initial situation. And it's got some kinetic energy initial is 40,000 joules. And the spring, I guess, is in equilibrium. Sorry. Got to spell equilibrium, right? So X initial equals 0 for the spring. And then finally what will happen, it compresses at 3.3 meters and stops. What can you learn about the bumpers at spring using this information? So the final situation is that the spring is now compressed some distance, X final equals 0.3 meters. And the car has stopped. V final equals 0. What can you learn? Well, you can just say that K initial plus U spring initial plus the work external equals K final plus U spring final. So instead of using gravitational potential energy, I'm just using the spring potential energy in the same way. So, so this one is going to be positive. The spring is initially at equilibrium, so it doesn't store anything. And then finally, all of that energy is going to transfer. So it's K initial plus 0 work equals 0, because it stops, plus the U spring final. So I've got 1/2 m, well, actually, I'm not going to do it that way because I was given it, right? Just K initial is equal to 1/2 times K times X final squared. So there's two K's. Lowercase k is spring constant. And uppercase K, with the I on it, is initial kinetic energy. I guess we can find this. So you could say that lowercase k is equal to 2 times K initial divided by X final squared. So it's actually 2 times 40,000 divided by 0.3 all squared. I get the spring constant of a spring that can stop a car is 8.9 times 10 to the 5 newtons per meter, which is a very stiff spring, sort of industrial kind of spring, which I guess you would need to stop an actual car in 30 centimeters. So I could just say that is a very strong spring. Okay. Doing for time. Doing all right. How's the discussion board going? Okay. Let's finish up with potential energy. I've got a couple more slides on that, and then we'll get into the friction question that we were asked about. Okay. Yeah, so basically, this is just showing that you can make a graph of 1/2 kx squared, and it looks like a parabola if you plot potential energy versus distance. 1/2 k times x minus x equilibrium. So there's going to be some position where the spring is unstretched. If you compress the spring, the potential energy goes up. If you stretch the spring, the potential energy goes up. So it's this curve with a minimum at xe, the equilibrium length. This curve is determined by the spring constant. You can't change it. But what you can change, I guess, is the total energy of maybe a mass on the end of that spring. So if the total mass, the energy is that horizontal line, that kind of red line there, then what can happen is that the object can actually oscillate back and forth from this height to this height. And so when it gets up to here, when these two paths cross, that's when kinetic energy equals 0. So kinetic energy is always the difference between the total energy minus the potential. So it's going to be fastest when it's at equilibrium. It's going to be 0 when these two things cross. So this is why a mass on a spring will oscillate back and forth, is because you've got the kinetic energy being this difference, going to 0. See, these are turning points when it gets to the end. So it's one nice way of looking at motion of things. If you have a more complicated potential energy curve, like a hill or something, and you release a particle from rest up here, where kinetic energy equals 0, then you can see right away it'll speed up to get to a maximum speed when it gets to x2. And then it'll keep going. It'll get to a minimum speed at x3. And then it'll go even faster, to even a faster maximum at x4. And then it'll keep going until it gets to x5, and that's when the kinetic energy goes to 0, and so it'll have a turning point at that point. Reverse the motion after it gets to x5, and it can go back and forth that way. But if there is some dissipative forces as it travels, it'll tend to settle. It'll either settle at a local minimum, like x2, or at the global minimum over at x4, one of those places. And those are called stable equilibria, because if you disturb them, the potential energy goes up, and so the kinetic energy goes down, and so it tends to turn around, oscillate around these minima. And if you look at, for example, in chemistry, there's certain molecules like hydrogen. Hydrogen, if you have hydrogen gas, like these balloons that they always, at Science Rendezvous, in between the physics building and the chemistry building, this is in May, the chemists come out with their hydrogen balloons and they light them on fire and they explode. Now in physics, we don't do that. We don't mess with hydrogen because we're just too scared of it. We have helium, but it's not flammable. I don't think we have any hydrogen around. Do you? No, it's too dangerous. But the chemists do it. They'll blow it up. They're completely crazy. But what hydrogen gas is it's actually two hydrogen atoms, so two protons, and they come to a particular equilibrium distance away from each other, which is about 0.1 nanometers. And the reason they do that is because of this potential energy curve. So this is the atomic separation between the two nuclei, the two protons. There's a minimum right here, and that's where an H2 molecule tends to sit. So the energy is it's electric potential energy, but which we don't get to till physics 132. But it's the same sort of idea. You're finding U is some energy curve, and then if you have a particle at that point, it wants to settle at its equilibrium length. Okay.
Professor, we have a question.
Let's hear it.
It says, would it matter if x was ever negative to the left of equilibrium, or does it not matter since it gets squared in inelastic potential energy?
That's a great question. Yeah, exactly. So the x squared in the spring potential energy is always positive. So if you're either to the left of equilibrium, that might be compressing the spring. That's going to add energy. Or if you're to the right of equilibrium, stretching the spring, you're going to add energy. Either way. So it doesn't matter if x is positive or negative. It's a really good point, whoever typed that. Thank you. And thanks, Rhea. Okay, let's do another learning catalytics. This is getting on to friction. What the heck is friction? Well, this is how you stop your car. You start it by pushing the gas. You stop it by pushing the brake pedal. So what the brake pedal does is it is a little clamp which clamps on the brake pads, which are rotating, which are connected to the axle of the car. It slows down. As the car is slowing down, the kinetic energy is transformed into what? A, gravitational potential energy, B, elastic potential energy, C, internal thermal energy, or D, rest energy. So according to the vocabulary of this book, which is your best answer, think about that. Check with your neighbor. Okay. This is like a vocabulary question or something. What's the word we're using? Can you click in? Going once, going twice. And stop. And let's take a look. So yeah, that was the one I was going for, is internal thermal energy. It heats up the brake pads. That's why this thing works. So it creates a lot of heat, actually. It's all that kinetic energy of the car gets changed into thermal energy of the brake pads. Heats them up quite a lot. But hopefully not enough to melt the metal or something. So the question was on the discussion board, is energy always conserved? So I'm going to say it is, and here's how the book goes through this with we're into section 7.5, friction and energy conversion. It's a little confusing, so I thought I would just go through how the book reasons through this. And it's in the case of there is a box on the ground, and then someone's pulling it with a string some distance, and it starts at rest, ends up at rest, just goes horizontally, but it's moved some distance. So while you're pulling it, maybe at a constant velocity, if it's not accelerating, then the tension will equal the friction force of pulling it across, I guess, the floor. So you're both generating heat in the floor, and you might be actually scratching the hardwood a little bit too. So they've noted that it's warmer and scratched on the floor. And if you remember, when we had the infrared thermal camera that Pius set up, and I was rubbing the floor, you could see that it got heated up. So it's actually, I like to think of this energy as there, like, I don't know, I usually draw it as little wiggly lines, like there's hot coffee or something. Something is heated up, so I've left energy behind. So if we choose the box or a car as our system, then this friction is an external force. And so it just does negative work. And that's definitely one way of doing it, but I find it a little easier to just add it on the right-hand side as being some heat, because I like to think that that heat is there. It wasn't there before, but then you move the box, and now there's some heat left over. So I'm picking the surface and the box as the system. And then you have this delta U internal, which is always positive. It's that heat. And it's that friction force, so mu sub k times normal force, times the distance that it got dragged. So the equation I like to use is this one. And you can see I've tried to redraw the diagram so that the system now includes the carpet. So on the left-hand side, you've got initial kinetic energy, initial gravitational potential energy, I guess, and you've got any external work, like that, the tension, pulling it, that's external work, okay? On the right-hand side, you've got the final kinetic energy, final potential energy, and now you've got this new term, which is positive, F sub k, kinetic friction times distance. So there's multiple ways of doing this, but this is a way. And it's the way she does it in section 7.5 as well. So it looks like this. You've got, in the case of this guy, if it starts at rest and ends at rest, then there's no kinetic, and maybe you define the 0 point of potential energy to be the floor, sitting on the floor. So kinetic energy, initial and final, is actually 0. But what you're doing is positive work with that tension. And what that's balanced by is the positive final heat. So any work you put into it is just going to get dissipated away as internal thermal energy in the carpet and the bottom surface of the box.
Professor, there's a question from
Yes.
the Learning Catalytics. It says, why do car brakes get more squeaky in cold weather? Is there any relation with the thermal energy transfer from kinetic energy, in brackets, lower force of friction maybe?
Yeah, that's a good question. So when things get squeaky, what's happening is that there's some kind of oscillation that's happening at audible frequencies, like some sort of if it's 1,000 hertz that it's oscillating for some reason, then you'll hear this whee as it's going. So something must be causing it to resonate at some frequency. So that's kind of a complicated thing beyond this. I know that sometimes you have a stick-slip transition, like if you take a bow and you drag it along a string, then there'll be that an alternating between static friction, where the bow pulls the string, and then kinetic friction, where it slips. And then you'll go back and forth oscillating between kinetic and static friction, and that'll cause you to be able to play a note on a violin. And I imagine it's a similar thing with the brake pads. Something is sticking and slipping as it's going along, again, because of some changing in the coefficients of friction, and it's causing, like bowing on a violin string, causing this audible sound. Want to do what do you guys think about this learning catalytics? This is just what we talked about. Let's read it through. Yesterday in my office, I pushed a box, initially at rest, across the carpet to the other side of my office, where it now rests. Define the system to be the box and carpet, and also define the 0 point of gravitational potential energy to be the floor. I guess 0 when the box is on the floor. Also, the initial situation is just before I pushed the box, and the final situation is where it is now, on the other side of the office. So I think you're allowed to, I can walk around, but hopefully you can choose multiple answers on this one, if I've set it up properly. Choose all the things in this equation which are not 0 that you're going to have to get equations for and add them all up. How are we doing, guys? This is a whole new way of solving problems, is just picking which things are 0. Actually, it takes some practice, I think. And then which things you can solve for. So I do want to see how you did, so please try to click in. I think you have to submit after you've clicked all the things you think are not 0 in this particular example. 5 seconds. 4, 3, 2, 1. And I'm going to stop session. You guys got it? No objections? Ooh, not, sorry. Stop delivery. So I liked C and F were the only ones I thought were not 0. So it starts from rest and it ends at rest. That's why these ones are 0. Whoop. 0 starts. It also, we've defined the box to have 0 height. And so these are 0. Because I guess my office floor is horizontal. I'm not pushing it up the hill or down the hill. So the only things left is this is the work I do on box. And this is this F sub k times d, how far I pushed it. Okay? So those should be equal in this case. So it's all about how you define the system. Whoop. So let's do a couple examples, or at least one. A driver slams on the brakes, locks all 4 wheels, and the car skids 18 meters on a horizontal road. The coefficient of sliding friction between the wheels and the road is mu sub k equals 0.8. How fast was the car going before slamming on the brakes? So I might try to draw it kind of like this. Again, it's kind of hard to draw cars, but I do it like that. This is the initial situation. Is V initial. Is actually a question mark. We don't know that. Then it goes along, Then it releases some heat. This is those squiggly lines I was talking about that sometimes you draw over hot coffee or something. And then at the end, you got V final equals 0. And this is sort of your delta U internal. It's all that heat that got generated. So this is the system. I'm going to choose the system is car plus the road surface. That's how I like to do that. So the way it goes is kinetic energy initial plus, I guess, plus work or something is kinetic energy final plus delta U internal. So if you wanted to draw energy bar graphs or something like that, it would be, it's got some initial energy, kinetic energy, it stops, and all that gets turned into U internal. So 1/2 mv squared plus 0 is equal to the kinetic friction force times this d equals 18 meters from here to here times d. So, and then I guess if we look at normal force mg and fk, the sum of forces in the y direction equals 0 is normal minus mg. So normal is equal to mg. So you've got 1/2 mv initial squared is equal to mu sub k times m times g times d. And we solve for vi. So I can immediately divide both sides by m, which is nice. Doesn't matter what the mass is. And we get, which is good because we weren't given the mass, square root of 2 times u sub k times g times d. 0.8 times 9.8. So it's not the only way of solving this problem, but it uses the energy techniques of chapter 7. 17 meters per second. And this is sort of typical highway speeds, I guess. I think it turns out to be about 60 kilometers per hour or something like that. So that's my sort of evaluate step. Okay, and I won't do this next example, I think, because I'm a little bit running out of time.
Professor, do we have time for one last question?
Yeah, I do.
Okay. So they ask, for the previous learning catalytic, why is work not 0? If other initial situation is just before the box is pushed, then how do we have work?
Well, there's no, at beginning it's at rest, and it ends at rest. So, yeah, it's sort of a good question. Somehow all the work that you've done has gotten transferred to just heating up the floor. Yeah, I don't know if that's a great question. So I do want you to finish reading up chapter 7, Gravitational Potential Energy in Space. And if you look at these two equations on the bottom, one is the equation we have for gravitational potential energy, and the other is the real equation. And I would argue to you that they're the exact same equation, just one is an approximation of the other. So we'll talk about that on Friday.